So if you want to become a solid developer, you do have to understand more than just the coding side of things, the programming languages and everything, because that is important because that's how we build things. But we also need to understand other skills. We need to understand how software at a greater scale, how software is developed, how to use other tools that allow us to become even better at building software, whether we're building ourselves or building as part of a team. So in this mini course, I'm going to show you how to use Docker to containerize your applications. Now, if you've never heard of Docker or you don't know what containers are, that's okay. In fact, I encourage you, even if you are in the beginning stages of programming, to actually go through this mini course. That way you have some ideas on what's out there when it comes to containerize software. That way you are able to take a piece of code or software, meaning being able to put your programs or your software into a box, containerized box that contains everything necessary for anybody to be able to run your software. It's an extremely fascinating technology, and that's what you're going to be learning in this mini course. Okay, enjoy. All right, so now let's go ahead and start looking at Docker. So it's going to be an introduction to Docker. So we're going to look at what is Docker and why should you care. We're going to look at containers and VMs. VM stands for virtual machines, as well as the benefits and use cases of Docker. So definitions are very important because it kind of conceptualizes the whole idea of something into words. So let's do this. To define Docker, Docker is a software, but most importantly, it is an open source software development platform that allows us developers, people who build applications, right, to develop, distribute, and deploy applications to make this whole process as easy as possible. But at its core, Docker really shines at making sure that we package our applications into what we call containers. Now, the great thing about this container is that they can run on any OS. OS stands for operating system. Now, you may be thinking, well, this is a wonderful thing. Of course, it's a new toy, great technology, right? But the question is still the same, is, okay, why is this important? Why do we even care to talk about Docker? So we just said that Docker at its core allows us to package our applications into containers, which these are the things per se that are then run on any OS. And yet we have another question. Okay, if that is true, then why is this so important in software development? So essentially, what problem does Docker solve? This is where what I'm going to show you now, hopefully it's going to help you understand the importance of Docker. So imagine we have a developer here. So what does a developer do? Well, a developer writes code locally. When a developer writes code locally, the developer tests, and of course, when they test, everything runs smoothly inside of their machine because they're testing everything. They have all the dependencies. Everything's great. Now, as you know, when we develop applications, the intention is not so that we only run it on our local machine. The intention is to share our code with testers and everybody else in our organization so that way they can test and do all sorts of things that need to be done before deploying. Now, when this developer pushes this code to, let's say, testers who are running or have the window environment running on their machines to test this code, what would happen is the code is going to be sent, of course, the whole environment, let's say Linux, Node.js, libraries, etc. Everything that allows this application to actually work is going to be packaged up and sent out, right? And then, of course, the testers are going to go and run application, but there will be a problem because now we are in a different environment. This is not going to work. So the testers won't be able to run this application when they try to run it. So it all fails to work because, again, of the environment and the dependencies, as well as the libraries that may not work on a Windows environment, as an example. So this is when Docker comes to save the day with Docker containers. So what happens now? Well, the same thing happens. We know developer writes code on a local machine. compiles that code because it has all the dependencies, everything that needs to run, and tests locally. Everything runs beautifully. Now, the difference here is that when the developer sends the code, he's not sending the code itself. He's actually sending the entire environment that needs to run this application. So now, because we are containing, in this case, we have a container that has the libraries, the running environment, everything that is needed, the dependencies that are needed for this application to run, all that is packaged up and sent to, in this case, again, the window environment for our testers. And guess what? When they run this application, it's going to be able to run because Docker container has all of this environment set up for this application to run, independent of what environment do they actually have. In this case, window environment. It doesn't matter because this container here, as you can see, right, it has everything that is needed for this application to run. That is the power of Docker. So now you can see that Docker, in this case, Docker containers, as they call, have a lot of different benefits. So one of the benefits that it has is that now Docker containers work everywhere and run the same. No longer do we have to think, okay, what libraries do we need for this application to work? Okay, we have to tweak X, Y, and Z to make sure it works on Windows, and then we have to make sure that it works on Linux or any other operating system. No, there's none of that anymore. All we have to have is actually having Docker as a system, as a platform running on that system, and then that application will be able to run independent of the overall operating system. So again, no compatibility issues anymore. So we have that predictable behavior on how the application should run. And of course, this is less work because, again, as I said, no need to configure things here and there. So everything just works. Okay. And of course, it's also easier to maintain and deploy because, again, all this abstraction is out of the equation. All I have to focus is just testing the code and package everything and go. The beauty also of Docker containers is that they work with any language, any OS, and any technology. Because remember, it's a contained container. It's a contained environment that has everything the application needs to run. And there we go. So I hope with this very short introduction, you understand the importance of Docker. Why is it important for software development, for deploying and maintaining large or even small scale applications? Because now we have this contained environment that we can ship to anyone else, any other team in our organization or anywhere else in the world, really, as long as they have a Docker environment running, they're going to be able to run any application because this application is going to be contained in a container which has all of the tools, all of the dependencies, everything it needs to run consistently. So now we understand what Docker is and Docker containers, what they are and why they're so amazing and important. Because the idea is still the same, is that we Dockerize, we containerize, we take this code, this application that's running in one environment, and we take all the dependencies, put all together, and then we create a container out of that. So we have this entity that can run anywhere, right, in different environments, and that is awesome. But the thing here is that this is mainly on the development side of things, these benefits that we get. But we also have other flexibilities, other benefits we get on the other side. So in this case here, we get other benefits when it comes to the deployment side of things. Because if you want to deploy an application to the server, in this case, a Dockerized or a containerized application to the server, we can also take advantage of Docker, the capability that we already learned, right? Because in this case here, we have this containerized application, right? And then it's ready to be deployed. So we can easily deploy and run Dockerized application on any server as long as the servers have the infrastructure set up. And now the instructions that are needed to make this happen, to deploy this Dockerized container application into server or servers, are a little bit simpler. So first step is going to be go ahead and provision a running server. So that could be an Ubuntu, it can be just straight up Linux or anything, doesn't matter. And then the second step would be to install all the dependencies that would be done. And then the third step would be to configure the system. And then number 4, to copy the deployment binary, and then of course run with those options that were set. So all of those instructions are set up, and all we have to do is just deploy that to our server, and then life is good. So you can see the advantages now. Now, it may be difficult to see this as advantages, because if you've never had to deal with deploying application on different servers that are running different softwares, different environments, it's very tedious and takes a lot of time, because there's a lot of setting up that needs to happen before we deploy the application. Now, when we have a Dockerized or a container, in this case application, that is ready to run, to be deployed, it's way easier, because all of these instructions, all of these things that we must or we needed to do before to make sure that these applications would run correctly on those servers, now all of that is abstracted out, because all of those instructions can be added or running, in this case, inside of that container. So it's way easier to set things up. So instead of waiting or spend hours and hours to set up the servers, go through all the list of instructions that need to be done to prepare for the application to be deployed, now that can be done in a matter of minutes. So in summary, here are some takeaways. When we use Docker containers, we are simplifying everything, essentially, right? So we're simplifying the whole system that's related to running and deploying our applications. Because now with Docker running, in this case with containers, the Dockerized applications running, we have a much more simplified, unified, and secure approach to putting together, to building and deploying applications. And this is very important, because all these steps take a lot of planning, a lot of time, a lot of man-hour, a lot of work to get it right for applications to actually run on different servers, different environments. But with Docker, right, this containerization of applications, all of that is thrown out a window. So now we can only focus on building amazing applications, and then leave all of this provisioning, all of this creation, all of this containerization of our application to be taken care of with Docker. So essentially with Docker containers, we have abstracted out all of necessary steps that we would have to do in order to have our applications running on different operating systems, right? Because now everything is contained. And on top of that, on the other side, which is the deployment side of things, things also got way easier, because now we have a unique way of doing things, more simplified, more unified, and most importantly, secure approach to building and deploying applications without having to do a lot of ground work or leg work to get everything set up with the servers. Okay, so I hope that you are seeing the big picture of Docker and this technology, which is an amazing technology, especially when it comes to running and deploying applications. Okay, so we're going to continue learning more about Docker in the next videos. Okay, so now let's look at Docker containers and virtual machines, so VMs. So particularly, we are going to look at what is a container, and we are also going to understand how internally Docker works and how also virtual machines work. So what is a Docker container? A Docker container is a very lightweight executable file, or package in this case, that is a standalone. So that means it's a container that is unique, that doesn't need anything else, because everything is packaged inside of it. Okay, so it's essentially a software package that has everything that is needed to run an application. Now, this Docker container, as we've seen before in this picture, something like this, as you see here. So a container in this case would have to have certain things, because we said it has to be itself a self-contained environment, right? A standalone, a lightweight standalone executable environment, a software environment that has everything for an application to run. So it has to have a few things. First of all, it has to have all of the dependencies that are needed to run that application. It also has to have what we call the runtime dependencies. So it could be Python environment, a Node.js or Java environment, or Go environment. It doesn't matter. right? So it has to have, obviously, its own runtime so that it knows when or how to run the code, this application. Okay. And of course, it has to contain the application code. So think of a Docker container. You have your application code, and then the runtime in which this code will run, as well as other operating system dependencies that are needed for this to run. So it has to have all these things. And one thing to remember is that now, in this case, we have this one nice box interface we can run to create multiple copies of the same application with one single container. This is the beauty. That means now with this container, we can go ahead and run it on server A if you want to, and take the same container, right? Run on server B and so forth. Now, the next thing we need to look at is the difference between a container and an image, because this is the part where we're going to look at the lingo, because that's very important, the language, so we understand exactly what's happening. So in order for us to have, in this case, an actual container which can be run, we need to have an artifact, which in this case is called the container image. So a container image is the file or files that have all of the dependencies that are needed to actually create the container to be instantiated from it. So essentially, a container in this case is what we run from that container image. This would be a container as we've seen. So everything is packaged up and it actually can be run. Now, I love analogies and I think it's the best way for us to learn. And so I like to think of a container image and a container in the using object-oriented programming analogy. So if you think about it, in object-oriented programming, we would say that an image, in this case, a container image, is a class. And a container would be the actual object, which is the thing that we've instantiated from our class, in this case, our container image. Now, it's really important to understand this difference between the container image versus the container, because it's easy to get those two mixed, but just think in these terms if this helps. And also, you'll see us saying image instead of container image. So when I say image, so whenever we want to reference a container image, we say just an image instead of container image. But it is the same thing, container image, or just image, we are referring to the same thing. So most people just call it an image instead of a container image, but it's the same thing. Okay, just another little thing to keep in mind. So to understand Docker, we need to go back and look at virtualization and virtual machines, and essentially how all of that works. So here's an example. So when we run applications locally on our computer, so if we open our computer and decide to open up, let's say, Photoshop. So what's really happening is that we're essentially utilizing what's called bare metal layer. What this is we would have a computer, as we see here. This is our local computer, and then we're running directly on the machine. So the application that we are opening, or applications, they're all running on top of our machine, on our machine directly. So if you look at our host, in this case, our physical machine, we have the physical hardware, and then we have the operating system, which governs the entire system, really, the entire computer. And on top of that, we have these binaries and libraries, which are just simple, well, I shouldn't say simple, which are pieces of codes or software that are able to make it so that these applications that we run can actually run on top of our operating system. In summary, we would have, in this case, the physical hard drive, and then on top of the physical hard drive, we have the operating system on which these libraries are installed when we run those applications. So in this case, we can have application 1, app 2, app 3, and so forth. So we're running this locally and all is good. Now, even though this is acceptable, this is how we run our applications on our machine and it's fine, but there's some issues with bare metal way of running applications. So first of all, there's issues with dependencies conflict. So what that means is there's a term called dependency hell. So what this means is that the dependencies and libraries have to be shared across all applications when the applications are running, which is problematic. For example, let me go through so I can show you everything. If we have, in this case, app A that is running, and this application needs an update version of dependency X or library X in the system, and or application B or app 2 needs, in this case, a different dependency to in order to be able to run. So you can see now we have issues. We either have to modify our applications, in this case, to conform to the installed dependencies that are already running on the system, or figure out ways in which these dependencies that we need to install hopefully are compatible with these two applications that need those dependencies to run. You can see that this is problematic, to say the least, because now we have issues with dependencies conflict that are really hard to pinpoint and fix. And the other issue we have with running applications on bare metal is that we have what we call the low utilization efficiency. What this means is, because of the dependencies fiasco that we talked about above, it really is hard to install and run more application on this same machine, because it's hard to utilize the power of the CPU effectively in this environment due to the challenges of dependencies conflicts that we talked about. Okay. And the other issue is that we have what we call large blast radius. So when we talk about large blast radius, it means if something happens, so issues from application A, we say it has some problems, it's not running correctly. These issues that arise from application A or one having issues, well, that could propagate or can directly impact the performance of application 2 or application 3 or any other applications that may be running. The reason being, again, is because everything is being shared when we talk about a bare metal architecture per se. And with that, of course, we will have very slow startup and shutdown speeds, because the whole system becomes very slow when trying to shut down and start things back up, because again, we're sharing everything. All the applications have to share resources. And it's also very slow to provision and decommission certain applications that may be running, because it's difficult in this case to create, in this case, provisioning, it's create, right, instantiate more machines, in this case, host machine, will be very slow. So in this case, you need to order new machines, set up servers, more installation configurations. So it is a lot of work, even though it works because it's bare metal. That means we can just install applications, but then it comes with problems. So this is what prompts engineers to come up with a better solution in this case, which is called virtualization. So we still have our host machine, but something is different. So we still have our physical hardware, but then we have what we call the hypervisor. So the hypervisor, it's what sits between the physical hardware and, in this case, the virtual machines, which contain, each virtual machine contains its own environment, in this case, the libraries, binaries, and guest hosts to run those applications. So now we have this separation, in this case, of environments per se within the main environment, which in this case is a virtualization of these little machines. So essentially we have one machine, 2, 3, and 4, as many machines as we want, because these are virtual machines which have a guest OS and all of the things, all of the dependencies needed to run those applications. So this is the solution, right, called virtual machine. So the advantages over bare metal machines is that now we have, again, the hypervisor layer, which allows the creation of a sandbox, right? A structure that has all the tools, all the dependencies, all the resources for apps to be able to run independently, right? So in this case, we're going to be focusing on memory, CPU, OS, binaries, virtual hardware, and so forth. So we have these containers, virtual machines, that they are their own entity that can run those applications. So it's better than what we had before. In this case, now we can create many of these sandboxes to run our applications, as you can see in our example here. But also, the great thing is that we no longer have the dependency conflicts, because, as we said, virtual machines are their own entity that have their own guest OS, everything that the application needs to run on its own. So that's really good. Better utilization efficiency, because now we are not fighting these virtual machines, or applications are not fighting for the same resources because they have their own resources in their own boxes. And of course, it's faster startup and shut down, and faster to put together, to provision and decommission each one of those virtual machines, because we're not fighting again for resources. Now here we're emphasizing the advantages we have with virtual machines over bare metal machines. Now it's also important to notice that virtual machines, although better than bare metal, right, machines, they also have some disadvantages. So VMs are great, but they are not the best because they have higher utilization. So you have to have a lot of memory, CPU power, for these to work properly. And it's also higher size in terms of gigabytes, because each one of these virtual machines will have to have enough space for it to be able to run independently. And of course, higher boot up time as well, because of the resources that are needed. Even though virtualization or virtual machine is way better than bare metal, but there still are some challenges. So it is one step up from bare metal machines. Okay, so from this, now we have Docker and containers. This is where things get fun, because now containers are another level of virtualization. So we have more advantages over VMs, over virtual machines. Some of them are as follow. So now when we have, in this case, a container, well, let's look at the Docker structure container here. So we still have, of course, our physical hardware. We do have the operating system, but now we have this thing called Docker engine. This is what we call the container runtime. So what happens now is that we have a container runtime that sits on top of the operating system. So now the container runtime will then manage any of these containers that we may have here at the top running, right? And the great thing is that these are also independently running. So as you see above here, we have container 1, could have app 1, and has its bin, right, binaries and libraries and everything, because it's sitting on top of a Docker engine, in this case a container runtime, which will be able to orchestrate each one of these containers. So we have container 1 with app 1, has all the resources to run. We have container 2, app 2, that's running there with all the resources it needs, and so forth. Now, it's important to notice here, each one of these containers has its own binaries and libraries and applications running inside of them. Very independent. Now, the thing here is that each container runs on the same host, but the downside is that they're not completely independent entities from each other. Compared to what we had before, which was the bare metal, and then we went to virtualization, this is actually a better architecture for the reasons I'm talking about here. So now the containers are very lightweight, which means they're very small in size, okay? And there are no dependency conflicts as before, and even better utilization efficiency, right? Very small blast radius. So if something happens to container A or app A, it's not going to affect container 2 because it's its own entity, which is really good. That's what you want. Even faster startup and shutdowns because they are very independent and they're running, of course, on top of a Docker engine, which knows exactly what needs to be done to make sure that these are as independent as possible. Of course, not completely, but it abstracts out all of that issue, all of those issues that we had before. And of course, even faster provisioning. So you can go ahead and this container A or 1 is not working out. You can go ahead and decommission it fast in a matter of seconds and then commission a new one. Very, very fast. So next, we're going to keep looking at Docker and containers into more details. Wait, so even though containers are amazing over, in this case, virtual machines, but there are some downsides, obviously, to containers as well, but not enough to discard containers. So in this diagram here, I'm going to show you the trade-offs per se between containers and virtual machines. To the left here, you can see that for our Docker, we say that we have our Docker engine container running, which is the one essentially that is allowing these containers to be run, right, as their own entities. So each application here is independent, more or less. Each container here contains all of the dependencies needed in the application running on its own, right? Which is wonderful. But then you can see that, as we said before, this has very low utilization because there's no conflicts in terms of trying to get resources, because each container, with the help of the Docker container, in this case runtime, will have all of the resources needs to run. And also the size of memory that needs for running, it's very low, and boot up times is equally very low. The issues, of course, with, in this case, a virtual machine, as we saw before, first of all, the architecture is very different, although they share some similarities in terms of an overall architecture. But the underlying architecture is very different because now here we don't have a Docker engine container. Of course, we do have a hypervisor, and we saw earlier there's some disadvantage to this. One of which is that utilization is really high, as well as the size that is needed of the hard drive, as well as memory, to run multiple virtual machines, okay, where the applications will run. And of course, because of the resources are shared, in this case, boot up times will also be pretty significantly high. So essentially what VMs lack, containers excel at. So you can see that Docker containers are way better than, in this case, virtual machines for the reasons that we just discussed, right? Because they're more flexible, lightweight, effective, and so on. Now, the question is, why would we use containers? What are the advantages, or even more advantages, we get from using containers versus just going straight and use virtual machines? Well, containers offer a lot of things. Well, first of all, they offer what we call a logical packaging mechanism, right? So we're able to package a sandbox, essentially, that has everything the application needs to run, its environment, libraries, and so forth. So then that means we have an easy way to develop, to create those applications, as well as deploy those applications. In this case, they're containers, right? The application runs inside of containers. So we have these container-based apps that can run regardless of the target environment. So that is the beauty of Docker, the beauty of using containers, because now we're not just married per se, or the application is not just married to the development environment. Now we package it up, all of the things that it needs to run, and we can ship it to any other system, server, or machine, and things will run predictably. And also the creation, talk about being predictable, the creation, of course, of a predictable environment. So we're isolating the applications that are running from other applications, so we have a predictable environment for these applications to run, which is a desirable thing when we're running many different containers, many applications on a certain server or machine. And also the ability to run these applications anywhere we want. Of course, this is the main selling point when it comes to containers, Docker containers. So in a nutshell, if you think of a container, just think of it as a logical packaging mechanism, as I said, in which applications can be abstracted from the environment in which they actually run. So now there's this thing called decoupling, right? Decoupling, it's making sure that there's no dependency between container A and container B. They are their own entity. So this decoupling allows a container-based application to be deployed easily and consistently, regardless of whether the target environment is private data center, the public cloud, or even a developer's personal laptop. That is the beauty. So this gives developers the ability to create predictable environments. So these are very important keywords. Predictable environments that are isolated from the rest of the applications and can be run anywhere. So from an operations standpoint, you can see that apart from portability, containers also give more granular control over resources, giving your infrastructure improved efficiency, which of course can result in better utilization of your compute resources. In summary here, what we're saying is that first we have the bare metal. So there's no virtualization here. So computer is running directly on the hardware. So this is actually the most performant way to run applications. But as we saw, we have some inflexibility, right? So we don't have a lot of flexibility because you can only run one application per server. And also you cannot easily move application to another server when it comes to bare metal. When we have virtual machines, things are a little bit better because now we can run multiple applications on a single server or computer because we have that layer called the hypervisor layer, right? So this, although better, is not as performant as bare metal, but it's good. So there's a lot of good that comes from virtual machines. Virtual machines, the great thing is that they provide that isolation between applications that we always want, because you can actually run different applications on different virtual machines with no issues. But that is not enough for what we really want, because containers now come to paint a different picture, a better picture when it comes to running applications, deploying them, and so forth. Because now we can run multiple applications, single server or computer, just like in this case in virtual machines. But now we have what's called the Docker engine runtime. We don't have the hypervisor because it has its downfall as well, as we've seen. So this is way better than VMs because we can run many apps without worrying about the limitation of the hypervisor. So now we have a structure where each container runs on top of a container engine, in this case, the Docker engine runtime. And we also have this isolation between the applications that are running because they have to be their own entity. If something happens to container A, application A, then it's not going to affect 10,000 more containers that are maybe running on the same machine. All right, so there we go. So that was the overview, very deep overview of containers, bare metal, all of these different virtualizations that developers, engineers had to overcome to get to where we are today with containerization or containers, Docker containers, and the benefits. So it's important to understand these things because now we understand, okay, that's why, in this case, Docker is such an amazing tool, because for the reasons that I've shown you here. Okay? Well, thank you for sticking around. And next, what we'll do is we're going to start using our fingers and start creating, in this case, images and running containers with Docker. All right? I can't wait to see you next. Okay, so now we are going to set up our development environment so that we are able to proceed learning Docker. The things that we need to set up are as follows. So first of all, or most importantly, we need to install Docker. This in this case is going to be the Docker desktop app, which we are going to be using throughout this entire course. And we'll go into more details on what it does and how to use it. But the beauty of having Docker installed is that we will just have it run on the background, and then we are going to be able to use all the other things that we need to run Docker, create images and run containers and so forth. Now, if that makes no sense, it is okay. That is exactly what we are here for. That's what we're going to be learning in this course. And we're going to install, if you don't have this installed already, VS Code. This is Visual Studio Code. It's a very lightweight IDE, which I use in this course. Now, if you already have it, of course, go ahead and use that when it's time. If you don't have it, I recommend you install it. If you don't want to use that, you can use any other code editor. Remember, this is not a programming course. Nevertheless, we need these tools. Okay, and then of course we are going to be using Python in this course, but most of the things that we're going to be doing in this course we could have done as well in a different environment such as Node.js and so forth. But Python is just easier to get going, and that is fine. Last but not least, we need Git. You should have Git installed on your machine, or if not, you can go ahead and look ways to install Git. So Git in this case is going to become more apparent later when we want to create a workflow, in this case a CI/CD workflow or pipeline, including AWS and other providers and so forth. Okay, so those are just tools that we need for this course. the first thing I'm going to show you here, at least I have this link here, which is going to take us to one of most favorite places on the internet when it comes to setting up Python. Okay, so Python of course, runs on different operating systems. So if you're on Windows, Mac, and Linux, you can install Python if you already don't have Python installed. Okay, this is just a development environment setting up. So I'm going to show you this link here. I'm going to click on it and show you how to navigate this link for you to be able to install Python on your machine if you don't already have that installed. All right, so once you click that link, you will end up here. So kingsta.com, knowledge base, install Python. As you see here, this is very comprehensive document that allows you to go through the process of installing Python. As you can see here, it says how to install Python on Windows, macOS, and Linux. So if you're on Windows, of course, you're going to go down here and there is table of contents where you can just click and learn more about everything and how to install on different machines. So if you're Windows, click here. It takes you straight to Windows installing process. So I encourage you to follow exactly what they say here, and there's a reason why I have this link, because they do such a great job showing you how to install Python. So go through this, read through, and do exactly as they tell you or as they recommend here. It's very, very important, and just do that. Okay, so if you obviously are on a different kind of machine, let me go back up here. For Mac OS, click here and go again through the process here. Okay, and same thing, of course, if you are in this case using a different operating system, let's say you are on Linux, click there and go through the process. Okay, so go ahead and do that, and I'll see you next. Okay, next I'm going to show you how to install Visual Studio, or at least direct you to the right place. If you go to Google and say VS Code, usually the first link that you see here, that is what you need. Go ahead and click the first link or just go straight to download, and voila. So you can download here depending on your machine. There is Windows 10 and 11, and go ahead and get the correct installer that you need. Okay, so if you're Debian or Ubuntu, or Red Hat, Fedora, or Mac OS, then you go there. Now make sure for Mac OS indeed we have the Intel chip and Apple Silicon chip. That's very important because those at the Intel chip are older generation, I would say, Apple products, in this case Mac OS product, and Apple Silicon is the newest one. So if you have M1 forward, then most likely you need to go with Apple Silicon. Okay, and right, so just go ahead and download Visual Studio if you don't already have Visual Studio. Remember, this is just so that we are all in sync, but if you have a different IDE that you can't live without, of course you can use that. But I find that Visual Studio is a really good IDE for you to use, and that's why I'm showing you here. Perfect, go ahead and download this if you wish to do so, and I'll see you next. So now we're going to go ahead and install Docker. In this case, it's going to be the Docker application, the Docker desktop app. So if you just go to Google and say Docker, of course, you can go ahead and click on the first one here to learn more, but that's what we're going to be doing in this course. But if you scroll down, you can see you have this Docker desktop. So click on this. Now, the thing that I like you to do is to scroll down here and go to this download and install, because this is going to give us a lot of more of documentation on what is needed for you to install. So go ahead and click there, and this is what you should see. I'm going to make this a little bit larger for you to see. So here we can see that we have the Docker overview, the get Docker, get started, and all this great stuff. So you can read around if you wish to. And most importantly, we can see here we have the Docker desktop for Mac. If you click here, if you're on Mac, then this will give you everything you need to know on how to install and what are the system requirements that are needed. And that's very important to also keep in mind, as you see here. And here is the important part also called system requirements. So if you have, again, Mac with Intel chip, then make sure to read this to make sure it makes sense. It says it's supported version on Mac OS, and at least 4 gigabytes of RAM and all of this. Okay. If you're on Mac Apple Silicon, of course, it's very easy. You can just go ahead and install this way, or you can just install by install from the command line, as they say here, or install interactively, as they say also here. So in this case would be how we did earlier. Okay, so you can go back here and just click for Apple Silicon or Intel. So this will download the actual executable file, which you can double click, and of course, and run this, which you can double click and then install on your Mac. That is how simple it is on Macs. Now on Windows, unfortunately, it's a little bit, I wouldn't say complicated, but it involves a little bit more of tweaking things. So what you will do here, I'm going to click install on Windows, and I would encourage you to please make sure that you read the system requirements, but that's very important. And I will keep on WSL2 backend. Okay, and make sure you have this Windows requirements 1164-bit, and follow the recommendations and read everything here, and how to install and how to start the Docker desktop. As you see, it's going to be an executable file, right? You can double click and then it starts and it runs in the background, which is wonderful. The great thing about the Docker desktop, when you install it, you don't have to worry about anything, right? Because it will install the actual application. As you can see, it's a desktop app, which will be running in the background once you start it. But also, most importantly, it will install the CLI, the command line interface, which we will be mostly interacting with. Right, so we can do things with Docker and create container or create images and run containers and so forth. So that's the beauty of, in this case, going straight and using the desktop application, the Docker desktop application. Okay, again, this is an important step, so please don't overlook this. If you're on Windows and Mac, or also Linux here, you can click here and follow exactly what they say. This is the documentation that they have, and make sure you go through the process, make sure you have the right requirements, and go from there. All right, so once you have installed it, go ahead and run it. They explain everything, and you should be set to go. All right, so once you have Docker installed, as you see here, I am on Mac. So what I want you to do is to run the Docker desktop application. So for me on Mac, I can just go ahead and say Docker, just find that app, that application icon. We can go straight to the applications folder. If you're on Windows, of course, go and find Docker icon application and double click. It will start running in the background. So you can see here, we have this icon here. If you click, it should say something that says Docker desktop is running. Okay. Now, there's a lot of things that will happen here, but it's okay. And then you can go to the dashboard. This will open the Docker dashboard. Now, mine is saying something that I need to reapply configurations, but let's ignore right now. So there's a lot going on here, as you see here. And we have here containers, we have images, we have volumes, we have the dev environments, and all this great stuff. Okay, so we'll learn more about all of this. So make sure that at least you have Docker and that it's running. And as it runs, you can see at the bottom here would say engine running, in this case Docker engine running, because we have this icon that is a Docker icon, right? And you can stop from here, you can quit Docker from here, or you can just go back here and go to the bottom and quit Docker. Okay, desktop. Okay, so I just want to make sure that you have it installed and it's running. That's very important. And as you see here, if I go to containers, you can see that I have no containers that are running. If I go to images, there's one image NGINX that I downloaded a while ago, 12 days ago, and it's there. Okay, all right, very good. So make sure that you are able to run the Docker desktop application, and I'll see you next. All right, so now that we have some basics when it comes to Docker, it's time for us to see how all of this works, right? How to run a container locally. Now, this assumes a few things. First of all, you have to have installed Docker application, the desktop application. And before you do anything, of course, Docker related, always make sure that the application is running, and you will always see that the application is running if you have it showing at the top here. Now I have too many things going on because I have a lot of icons of applications running right now. You won't see here, but make sure you run it. So click on the Docker desktop application so that it's running in the background. Very good. So once you've done that, remember when we installed Docker application, Docker desktop, that is, what happens is that we're also installing the command line interface in the back end, which means we then automatically should have access, all things considered, to the command line. So open a command line or a terminal, depending on which operating system you are. Also make sure that you went through the whole process of setting it up, whether you're on Windows, Linux, or Mac. Okay, and when you do that, to test real quick whether Docker is installed correctly, right? All you have to do is just say Docker as such, and then you can run a very simple command here. Say Docker run and say hello-world. So what this will do, let's go ahead and just say enter. So what's happening now is something that is really cool. It's going to happen all the time when you are running, or in this case, trying to run a certain container. So in this case, when we say Docker run, here's what's happening is that internally Docker is going to look to find if that image, right? Because we need that image to run that container, right? So the image is a class. If we look at itself, will be the implementation of that class or the instantiation of that class, the actual object. Okay, so it will look to find if there's already an image installed locally, and if not, it's going to go ahead and pull from library hello world. So all of this is being doing in the background. We don't have to do much. So it goes ahead and pull that image, and all the images that are pulled in have an ID such as this. Okay, and there's some information there, and then later says status downloaded newer image for hello world latest. So this is the tag. Okay. All right. And we know this is working now because it's supposed to say hello from Docker. This image shows that your installation appears to be working correctly. That's all we wanted to be assured of. That is, everything is working. Docker is installed correctly. Now, if you don't see this, then please go back and follow exactly what they show you to do to install Docker on your specific machine. That's very, very important. All right, so there we go. That was very simple. And now you know that everything is running. So now let's look a little bit about this Docker run hello world. We could have said Docker pull and then the name of our image. Now, the thing we have to think about here is as follows. Let's actually look at where all of these images, as we always call them, where all these images come from. So if you go to hub.docker.com, this is what you will see, more or less. And what you want to do, you can go to repositories, you can go to explore. By the way, see repositories, I have some of my own here. We'll talk about that later, but I want to go to explore. And here you can see that, first of all, these are all the images. This is a registry, image registry, where all the images go, or where all the images actually live. So internally what's happening, Docker is able, when we say Docker pull or Docker run hello world, it's going here and finding that image. And you can see there's a lot of different images here. We'll get into this later time. I just want to get us going for now. So we have this Alpine, NGINX, BusyBox, and all these images. Now, I'm going to search here for hello world. And as I type, you can see that I have here verified content, hello world. So I'm going to click on that. And voila, you can see that indeed we have this hello world, and we have a way of pulling the command that we need to pull Docker hello world image into our machine, so to run it. Now, you also notice the difference here. Here it says Docker pull hello world, yet here we said Docker run. So either way works, because as you can see here, if we had say Docker pull, we are inferring that we don't have the image, so we need to go ahead and pull from here, right? But if you say Docker run and then the image name, then what will happen is exactly this. So it's going to go and look internally. Remember, this is all Docker doing all the work in the back end, and look for that image with that name. So if we don't put a tag we'll talk about tags later. It's going to go ahead and get the latest. Okay, so that's what's happening. So if you say docker run hello world and docker poll for the first time, like this, the same thing will happen. The only difference is that in this case here, it will look internally first, and it won't find that the image is locally installed, so it will go ahead and pull it, right? As you can see here, pulling from library hello world. Okay, very simple. And what I want you to do as an example, even though, don't worry, we're gonna go deeper into all of this, just come here and search for any image and see, for instance, this one, which we'll look at later. See how can you pull this image. You don't have to understand what's going on, just practice that. And the other thing I want you to do is, I'm going to just go ahead and say clear. I want you to look at certain commands, or at least a list of commands that Docker provides for us to interact with images as well as container. So if you say docker -- help as such, you can see that it gives us all of these different commands that we have at our disposal, right? So we see run, so create and run a new container from an image. We have the exec, we have the ps, all of these we'll look into some at least. So whenever in doubt, just say docker -- help and you get all of this. Okay, so don't worry too much. We'll go over the ones that we're going to be using the most. Okay, very good. Go ahead and play around with this, and I'll see you next. Very good. So next we are going to dive a little bit deeper and look at a different image. So I'm going to go back to our Dockerhub. The image we're going to look into is going to be called BusyBox. Okay, so click enter, and you can see that we have this BusyBox here. Now we don't have to go into the details exactly what it is or what it does. Essentially, just think of it as an image. In fact, you can just click here and you can learn more about it. So different flavors, don't worry, we're going to look into that later. So what is a BusyBox? The Swiss Army knife of embedded Linux. So this is indeed an embedded Linux. It's between 1 and 5 megabytes. And so very small, very simple Linux that is put in a little box so you can just play around with it. And of course, we have different ways to run the BusyBox shell and all of that great stuff. So this is the image we're going to play with right now. So as you know, as you see now, we can copy this straight, docker pull BusyBox, or do what we did before, which was to run it. And then the system will know that we don't have that image, and so it would pull. So same thing. So I'm going to just paste in that command there, hit enter. And so what will happen now is saying using the latest tag because we didn't specify the tag. So there we go. You want to go ahead and pull the latest library, BusyBox, and we have the ID. Okay. Now you may say, okay, this is wonderful, but I don't see what else is happening. What can we do with BusyBox? Wow, very cool. So here's what we can do with BusyBox. We can just go ahead and actually send a command for it to do something for us. So I can say, again, docker run BusyBox such, and then I can say echo, which means display something, a message. What message we need to put inside of quotes as such. I'm going to say hello from here. Right? Hit enter, and you can see the BusyBox was able to spit out exactly that message that we added here. It's something that you can see that it's not very valuable at this point, but it's something that shows you that this actually works. Now we can do all sorts of things with the BusyBox. One of the things is, well, we know that this is a container, and we can actually go inside this container, right, into its shell, and do other things, or at least see what's inside of this container and maybe run some other commands, right? So all of these, by the way, all of these commands that I'm going to be writing here, you will have access to all of them in the resources folder. In order for us to go inside of our container and run other commands, in this case, we're going to go into an SH shell, so we can do more inside the BusyBox system, essentially, because that's what it is. We have to run something like this. We can say docker run -it. IT stands for interactive mode, and then sh, right? We want to go into the shell, so hit enter. So I have a problem here, is because I said interactive, but I didn't specify the name of our system, of our container. So that's good. It gives us an error and it says something was denied. All right, that's okay. Let's go back and I'm going to fix that. So after the interactive, the -it, we need to say BusyBox because we need to specify the name of our container. Okay, now voila. This sign here tells us that we are inside of our shell, this shell here of BusyBox, internally, so inside of our container, which is really good. So remember, this is a system, and so we can actually go and say something like this, ls for a list, and voila. You can see now we have this file structure for a Linux file structure. So we have bin for binary devices, etc., home and libraries. You can cd to home like that, and you can see that there's nothing there, right? And we can add a file. So I can say, for instance, touch names.txt like that. And if I say ls, you can see we can write into these folders here, right? And from inside here, I can even say something like that, ping www.google.com, and see I'm inside of this machine, and it's actually I'm pinging www.google.com, and you can see it's working. Okay, so I'm going to say Control-C to stop that, and I'm going to clear that. So I'm still inside, of course, of our shell. So I'm going to say ls, you can see I'm there, I can cd out, right? So now I'm back to home. If I ls, I can go, for instance, to root if I want, cd to root. Of course, it's not going to be, it's going to be empty. There's nothing there. I can cd out again. All right, so this is pretty cool. We're able to, in this case, go into the shell of our BusyBox system and peruse around, and you can see that this is actually a Linux system because it has this Linux file structure. Now, to get out of this, our shell, I can say exit like this, and voila, now we're out of our shell. Now, the next thing I'm going to do here is I'm going to show you a command. I'm going to say Docker, and I want to see, for instance, all of the containers that are running. So we say Docker ps -a to say I want to see everything that is running and that is not running. So in this case, we are seeing that we have this BusyBox sh command that it was issued, that was 2 minutes ago, and it was exited. And of course, we still have BusyBox that we ran earlier to say hello from here. And then of course, we have also this container, which was hello world, which we ran. Very good. So in this case here, we can see that all of them have exited, so they're no longer running, and when they were created, and the commands that were invoked. And of course, we have the image names, and most importantly, we have the container ID. So every container that we run is going to have an ID. So that way it's simpler or easier for us to say, for instance, I want to stop this container here, right? So I can say, or remove rather, we can say, we could stop if it was running, right? But since it's no longer running, then that doesn't matter. So I can say, for instance, Docker rm to remove, and then I'm going to say, just copy, in this case, that ID. And voila, you can see, because it was removed, it usually returns just that ID that was removed. Now, if I run that command again by going the arrow up, so that I don't have to type everything again, hit enter, you can see now that I no longer have this first container that was running. I don't have 2 left. Now you can imagine that you could have a lot of containers that have been running or ran, they have been exited, but I just want to get rid of them from our system. And then taking just an ID at a time can be very tedious. Well, don't worry, there is indeed a way of doing that. So to do so, to remove all of them at once, all you do, you run this command. Okay, so it's Docker rm for remove, and then $. Okay, so we're saying now we're running this command all at once. So instead of Docker PSA, we have a few flags here to force, and the idea is that we want to get rid of all of the containers that indeed have status exited. As you see here, exited, that's the status. So I want to remove all of those. So if I hit enter, then you can see we only had 2. That's why we receive back those 2 IDs. Now, if I go back to run PS again, you can see no longer we have no containers there. Now, I'm going to clear this. The other thing we can do if we want to get a list of images, in fact, I can, first of all, if I'm not sure about what commands to run, I can say docker again, --help. And voila, you can see, we're back here, you can see all of these commands that we can run. We have run, build, poll, all of this, and images. Images, it says here, list images. All the images that are around, they're going to be listed if we run this command, docker images. Okay, it's very helpful. So I'm going to run that. Let me clear this and say docker images, and voila. Now, the thing here is that once a container is running, remember that there is a difference between images and containers, right? So containers are actually the things that are running, as you know by now. So when we delete containers, doesn't mean we're deleting the image, because the image is still there because we could use again to run a container. So if you want to delete, in this case, an image, you will say docker RMI and then pass the image tag, or rather the image ID. Okay, so in this case, I'm going to copy this, hit enter, and of course, it's going to go ahead and delete, and you can see that this indeed was deleted. You can enter, you can see we no longer have the BusyBox. Okay, if I want to delete this next one, of course, we could have done the same thing around that command we ran before, which deletes everything, but we're going to just use this. Okay, so now you can see that that was deleted, right? And if I go and say docker again, images list, you can see that now is empty. We don't see anything. All right, very good. So you've learned a little bit more here. Learn how to remove an image. Now remember the difference here, RMI, right? So remove an image. That's important if you are removing an image in a past ID. Now earlier we saw to delete a container was docker remove RM, no I and then the ID. So that is the differentiation there. So what I want you to do again is to pull in some different images, right? So you don't have to understand what they do for now. Just go back and explore and see all these images, pull them in, and see also if you can run SH, right? Run in the interactive mode and get into an SH. And some of these images don't have that capability, but just give it a try and see what you come up with or what you see. Okay, very good. I'll see you next. Okay, so now we're going to do the same what we were doing, but instead we're going to pull an NGINX image and run that container so we can see how that works. Okay, so let's go ahead and do that. Now, this is perhaps going to be a little bit more involved, but also more rewarding because we're going to be able to see, start seeing the power of using Docker, using images and containers and so forth. So when we go back to Dockerhub, you will see without searching or doing anything, just go to Explore, you will see that in fact the very first image that shows up is indeed Alpine. We'll talk about that. But the second most downloaded, most pulled image is NGINX, as you see here. That tells you something. So NGINX, let's go click and see what this is. NGINX is simply a web server where we can actually use it to run websites. Okay. In a nutshell, that's what it is. Now, there are a lot of different supported tags here, but let's scroll down and look at what, of course, it says here, what is NGINX? It's an open source reverse proxy server for HTTP, HTTPS, and so forth. Okay, so lots can be done with NGINX. So how to use NGINX, and they give us all these different things. Okay, so this is the image we're going to be pulling in and then do a few things with it. All right, so back to our terminal here. I'm going to say Docker. I'm just going to go ahead and say run engine, so NGINX, and hit enter. So the moment you hit enter, that means we're going to pull the latest version because you can actually pass a tag. If you go back here, you can pass different tags, supported tags, right? You can say mainline, 1.2 and 5, and all these different things. We'll look into that later, but okay. So I'm not going to do that. I'm just going to say NGINX and hit enter. We'll do the same thing we've seen before. Can't find the NGINX locally. It goes ahead and pulls everything. All right, lots of things have happened. And you can see here, it just stays like this. And you may think, what's going on? It's hanging. It's okay. So what we're going to do here, I'm going to open, say, Command D for me to open another terminal. So what I'm going to do here, I'm going to say Docker ps-a just to see what will happen. So it's going to list all of the containers that are running. And as you know, we only have one container running from image NGINX, and we have the ID here. And most importantly, if I make this really small, you can see that indeed we have a few other things. We have the command, the entry point, we have created 3 minutes ago, and the status. And most importantly, we have these ports here. This 80-TCP or /TCP, this is the container port. Okay, we'll get into that in a second here. Now, then we have this names. Names is indeed just a random name that is given to our container. So it's really important whenever we run containers that we give names. All right. If we don't give names, then we get these random names that are given to them. All right. That's okay. It's running. Everything is great. Now, if we try to go to port 80, as it is right now, we're not going to be able to access our container, in this case, to run to see what our server is providing us. Okay. Because we have port 80. This is the port that is attached to the container. As from the outside, in our web browser, for instance, we're not going to be able to indeed go into that. But let's understand how all of that works. Now, what we have right now is we have our host computer. Okay. In our host computer, we have Docker running. And then, of course, we have the container that is running. Our NGINX is running. And the NGINX has port 80. That is the port of our container that's running, in this case, NGINX. So what needs to happen is for us, in this case, to be able to access our NGINX, whatever it has to provide, we need to actually go to localhost 8080, for instance. But for that to really happen, we need to map our port 8080 to the container's port 80 so that we have access to our container and whatever it has to offer. Okay, so this mapping has to happen for this to work. So to do that, we'll have to do something that I'm going to show you right now, which is we need to attach the -p flag and say 8080:80. So this means we're mapping the container's port to our localhost 8080 so that we are able to access indeed our container. That is what needs to happen. Okay, let's go ahead and do that. I'm going to go ahead and clear this. So what we need to do is I'm going to say Docker run. I'm going to run on detached mode, so -D, meaning that regardless of anything, that will keep running on the background. And then I'm going to say -P for port, and I'm going to say 8080:, and make sure that this has to be 80 because it has to be the exact port that the container is exposing. In most cases, in fact, in all cases, you should have that information. So if we go down back to our NGINX in Dockerhub, you will see some information here that it says exposing external port. It has to be something like this. So essentially, you say Docker run. You can pass your own name, which is something that we should do. So say --name. In fact, let's go ahead and do that real quick. Say --name, and we're going to give our own name and say web site like that, and then detach mode, and then the port mapping is going to be 8080 to port 80, and then I'm going to go ahead and just say NGINX, and I can just say latest. I'll leave it as it is. So now if I click run, you can see that it's going to start running our website. So if I go ahead and say Docker ps-a, you can see now we have two things here. This is the one that is still running, the old one, right? Status app 8 minutes ago. And now this is the new one, which is the NGINX image latest, because that's what we specified. And we have, most importantly, our port mapping. This is very important. So now it says here the 0000, that means local host port 80. That's going to be mapping to the container port 80, so that way we can see something. Now let's see if this is true. I'm going to go ahead and open a new tab, say localhost, and let's make sure that we add 8080, hit enter, and what do you see? We see a website running. Welcome to NGINX. If you see this page, the NGINX web server is successfully installed and working. There we go. So we were able, in this case, to quickly and easily pull in NGINX, right, the web server, and then we were able, of course, to map port 80, our localhost port 8080, to the port 80 for our container, which is running. That way we have access to the container, which in this case, it's a web server, which is serving as this nice web page. We can map the same port to a different local port. That's the beauty, because now I can say, for instance, I'm going to just go ahead and say arrow up. And this is the beauty. I'm going to say website -1. Everything keeps like that. And I can say, even I can just put 80 like this. So the port 80 from the actual container is going to be mapped to port 80 locally. If I hit enter, voila, that worked. Now, if I go back and look at all of the running containers, you can see we should have 3 now. So the previous one, this one, if I go ahead and refresh, you can see that's still running. Now I'm going to open another tab. I'm going to say localhost. And instead of 80, I can say instead of 8080, I can say 80 like that. And you can see it's still running because we said I'm going to run yet another container from the same image. But in this case, instead of having the 8080 local port mapped to 80, the container port, kind of hard to see there. Instead of that, we're saying that we want to map port 80 to port 80 on the container. And that's why we're still having both of them running with no issues. So it's customary usually to have the same ports from localhost mapping to the actual container. So if the container is exposing port 80, usually you want to say 8080 or 80, doesn't matter, but that is the convention usually. So mapping the same container or the same port as the container port that is being exposed. But as you can see, it doesn't matter really. Any port works. Now, if a port sometimes on your machine is being used by other applications, that probably wouldn't work. So that's when you probably would want to add a different port. That is very cool. Very cool indeed. Okay, so I'm going to go ahead and delete a few of these that we don't want. Now, the cool thing also is that if I go and say, I'm going to clear everything, and say Docker PS in general, and you can see now, I'll make this a little bit smaller, say Docker PS-A to see everything essentially. You can see that now we have the names that we can use, right? So if I want, for instance, to say Docker and RM to remove the container, I can go with the ID, but I can also go with indeed the actual names that we've added, right? When we ran this container. So I can use that, hit enter, right? It says that container is running, so it can be removed. In this case, we can force that removal. So -F to force, and voila, you can see that the website 1 should not work anymore. If I go to, I think this is the website 1, right, the 8080, it's gone. Yet this one should be still running because we're on 8080, or rather that was the 80 port. This is the localhost 80 still running. That means I can do the same thing. Just get rid of the website. And if I come here, refresh, that is also gone. Now, if I say Docker PSA, we can see that indeed we still have that main one running, but the other ones are gone. So the main thing to keep in mind is that to be able to access locally, we have to map the exposed port from the container to our localhost port. Okay. Now, we also learned that we can map multiple ports, meaning that we still have the host and our container is running, NGINX, we have the exposed port, and now instead of 8080, we can also have, for instance, localhost 5000 if we wanted to, or 80 as you saw, which is going to map to port 80 of the container, and we'll be able to see the contents or the website, the web server, whatever the web server, NGINX in this case, will be serving. All right, very cool. So what I want you to do is to run these containers again, NGINX, and see, change different ports and change the ports that you're mapping to the exposed port on the container and see how it all works. All right, I'll see you next. All right, so we've seen this before, but I think I need to officially put it here so you know exactly why the why is behind. So we've seen that if I say Docker PS, hit enter, we see that indeed we see the images, or in this case rather, we see that we have images. So this lists all of the images that are actually running, right? Now, if I wanted to stop an image, I can say Docker stop and then take either the name or the container ID. I should rephrase this. If I want to stop a container, you don't stop an image because that's not what's running. Okay, that's the distinction here. So in this case, I'm going to use the container ID and I'm going to go ahead and say stop. Now, if I go back and say Docker PS, you can see nothing is showing. Now, if I say Docker PS-A, this should show everything. So meaning it will show containers that are running as well as containers that are not running. So you can see this was exited, right? This exited while 10 seconds ago, yet I will see if I say -A. So that is a very important distinction here between PS-A and PS, just PS, as you see here. Make this a little bit larger so you probably can see. Okay? So that's important to know. Now, I'm going to go ahead and run again. Say Docker run. I'm going to pass a name, website, and I'm going to put it in detached mode. And because that is stopped, you can see, by the way, because that one NGINX container has stopped, you can see that this already says exited, right? So we no longer see that working. So that's essentially what is happening. So now I can just go ahead and delete that so we can have this one running. So let me go ahead and say Docker run website again, detached mode, and then I'm going to say P, in this case, say 8080, right? So I'm mapping the ports here, and I'm going to run NGINX and just say latest. Okay, so hit run. And now if I say Docker PS-A to see everything, we can see that we have this one is running on port 80, right? Or localhost port 80, which is mapped to the container port 80. So again, if we go to port 80, we should see this support server running and serving as this HTML. Now, if we wanted to stop our NGINX or this container, our container from running, our NGINX container from running, we say Docker stop and pass the ID, or in this case, the name of our website. So let's say Docker PS, voila. Somehow sometimes doesn't show, but now we can see we have, it's called website. So we can use that name to stop. So it's Docker stop website, hit enter. Voila. Once it returns the name, that means the command ran successfully. It may take a few seconds. If I come here and run, you can see that it's no longer running. Okay. Now, if I want to start again, I can say Docker instead of stop. I'm going to say start, hit run, and now it's running. If I go back here, refresh, you can see we're back, right? And of course, if I say Docker to see everything, -A, you can see that indeed the old one has exited. This one is still running because, as you see, it's still running because we restarted it, and it's there. Okay, so now we've learned how to stop and start a Docker container. So now we're going to look at Dockerfile and images. So essentially, we are going to learn what is a Dockerfile, and we're going to be able to create a Dockerfile, which essentially will allow us to create an image, which then we can run as a container. So lots of fun stuff, and let's go ahead and get started. So in order for us to create a container, in this case, we know that we need an image. Now the question is, how do we even create that image, which then is used to run the container? Well, first of all, we need to understand that an image is just a file with some text on it. So essentially, it's going to be a file, as I mentioned before, which will list all of the commands to actually create, in this case, the image, which then we need to run the container. So a basic Docker file has the following directives. So again, it's just a file, and we add the instructions to create that image. First thing that you will see in a Docker file is from. So this is a directive that allows us to set the base image. So in order for us to create our images, we have to base that image, new image, base that off of another image, right? A base image, as they call it, that is already created. We can just pull that from a registry. And then we have the run directive. So this is the directive that will execute a command inside that image. Then we have the work dir, which sets the working directory inside of the container. This is very important, which will then can say, okay, if the work directory is going to be /app something, and then everything else that we do, it's going to be added to that directory. Now, remember, this directory is going to be created in the container. And then we have copy. So this, as the name implies, is going to copy files over from the host to the image, in this case, which is going to be in the container. And then we have the expose directory, which will tell Docker that the container has a port that is listening from. Okay, it's a very specific network port that will be connected at runtime. And last but not least, we have the CMD, which is command. This is what will allow the container to know what commands to run in order to run the application. So essentially, a Docker file looks like this. So we can see here, we have the from, which sets again the base image, right? And then we have the work directory. So we're saying that, okay, the work directory is going to be in user /source app. So then the copy, as you see there, we're saying we're going to copy all the files to the container, but it has to be under the directory that we specified, which is the app directory. And then, of course, we have the run directive here, which we are installing. We're saying pip install. So this tells you that this is a Python project application. So we say pip install. So installing dependencies that are written inside of these requirements, that txt file. Now, you don't have to know Python for you to be able to grasp all of this in this course. Remember, this is not a programming course, but we have to choose some environment. In this case, it's going to be Python, okay? So that's what's happening here. And then we have to expose a port. In this case, it's going to be 5000. This will tell the port number that the container should expose, which is 5000. And then run the command cmd. In this case, it's going to say Python, then app.py. Notice here we say ./app.py because we know that the source, the working directory here, directory where all of the files for this application will live under app. That's why we're going to go to ./ and then go to app.py. So it's always important to know where we find, in this case, that file that needs to run, in this case, app.py. Okay, and it's Python because that is the command that we run to run a Python project. Very good. So in the next video, what we'll do is we are going to get our hands dirty and author ourselves a Docker file, which indeed it's going to be transformed into an image. All right, let's go ahead and do that. Okay, so I have this random quote one. This is the project I've created. So right now it's empty. And so what we'll do here is that we're going to create a very simple Python application, which we'll build up in the next videos. So as you can see, it's empty for now. I'm going to go ahead and say touch, and I'm going to say app.py. So ls, now we have that. I'm going to go ahead and say code space dot, and voila, you can see now we have our app.py, which has nothing. Okay, so the first thing I'm going to do here, and remember this, you don't have to know Python at all. You will have access to all of these files anyway. So the first thing I'm going to do is I'm just going to go ahead and say import OS, because that's what we usually need, but maybe we don't need that. So, and I'm also going to import, in this case, random, which we'll need at some point. Okay. All right. So to start with, really, I'm going to just go ahead and create a function here. So I'm going to say def main, and then before I have all of that, I'm going to create I'm going to create a list that contains different quotes, so that inside of our main here, I'm going to randomly generate quotes. So I'm going to say quote and use the random, and I'm going to say choice, and then I'm going to pass the awesome quotes list. So this will, each time we run this is called, we're going to get a random quote from our awesome quotes list. Very simple. And in this case, I'm just going to go ahead and print our quote, and then I'm going to just pass this here is equal to main. So there we go, nothing out of this world. And what I'm going to do next is I'm going to create a new file here. This is where I'm going to create the Docker file. Now to create a Docker file, we have to follow exactly what I'm going to write here. So say d Docker file, and you see the moment I do that, we have the icon for Docker. So it has to be exactly like this, uppercase D and Docker file without extension. All right. Okay, so how do we create our very simple Docker file here? Well, for our Docker file, the first thing I'm going to do, I'm going to add directory from, it's going to be from a base image. So in this case, our base image, I'm going to say Python. And I want to go ahead and get the 3.11-Alpine. So we're going to go over that later. And you can see, because I'm using Visual Studio Code, I get some help here. So I'm going to use that one. Okay, so that is the base image we're going to base this application off. Then I'm going to add the work directory here. So for us, I'm going to just say this is going to be /app, like that. And then what I'm going to do here, I'm going to use the copy directory, source to destination. This is real nice. So what is the source? Well, the source is going to be this current directory, which is this one with all this information. And the destination is also going to be the working directories, which is app. So that's what we do. So put dot and dot. And then here is, we are going to install a few things, but for now, we're not going to do anything. We're not going to use the run command because we don't need to. Later we'll do that. Okay, so right away I'm going to go ahead and just pass the command to run this Python. Let's say it's going to be Python, and then it's going to be /app.py as this. Okay, because it's going to be inside of our app folder inside of our container. All right, there we go. That's all we need for our Docker file for now. So from directory, if I have work directory, we specify that, and we're copying everything from our current directory locally to, in this case, our working directory in the container when it's running. And then we invoke command to say Python and run the app.py. Now make sure, of course, then we are going to build this, but for that to work properly, you have to have Python installed locally on your machine. Okay, very good. Now we could also go ahead and run this, but locally right now, but I'm not going to do that. Now that we have our very simple application and we have our Docker file, as you can see here, we just created that. This is the Docker file. This is the file that's used to generate the image. So now we need to Dockerize this. We need to create the image, which will run these commands in our Docker file and create that image, which we can then run. And how do we do that? Well, good thing is, because we are inside of VS Code, I can actually open the command line here or terminal by saying control \, and voila, I'm going to close this down. And so we are in our directory where we have Docker file and app.py. So to create an image, make sure, of course, that Docker is running, right? So we need to run this command. First, I'm going to say Docker images. And you can see we have the NGINX image that I installed a long time ago. That's all we have. Right, so we want to build our own image, right? Create our own image using Docker file. How do we do that? Well, it's very simple. All you do, you say Docker and then build and then space dot. But this is not the best way to do it because we need to add a few other things to it. So what you need to do is say Docker build, and I'm going to say .t, and then I'm going to add, in this case, the name of my image. Let's call this rand quote, and I'm going to add a version. This is the tag that we attach to each image that's created. You've seen before that we have latest, but you can also add an actual number, because each time you create an image, you can tag different versions. Okay, so in this case, I'm just going to say 1.0. Once you have that, say space and the dot. Okay, this is very important. So Docker build -t, and then add the name of your image, colon. If you don't add this tag here, then it's going to be latest. So let's go ahead and add that 1.0, and then space, and then the dot. Hit enter. What will happen now is that the process will start where everything, voila, you can see, because we don't have a lot of steps in our Docker file, you can see we went ahead and ran 3 commands, right? So went to work directory. First of all, it was cached the library Python 3.11 because I've ran this before, so that went fast. And then ran the work directory, which is app, and then copied everything. In this case, all of these files, app.py and Docker file also included, right? If we had more files, we would add that as well. And then did everything that it needs to do and start exporting the image, started exporting to image. So exporting all the layers and writing the image and everything, right? So now if I clear this and I say Docker images to list all the images, you can see, voila, we have, it's under repository, right? Rand quote. And there we go. We have that image, which is 58.2 megabytes. So the question is, how do we then run this image? Because we want to see what will transpire, what will we get. So how do we run this? Well, to run, I'm going to say Docker run. I'm just going to go and grab the image ID like this. And voila, you can see that it went ahead and say every great developer you know got there by solving problems they were unqualified to solve until they actually did it. This is great. That means that our application is running. So we went ahead and got these last random, in this case, right? A random quote, because that's what we said in main when we run, just print a random quote from our awesome quotes that we have here. Look how wonderful this is, right? It is working. If I were to run this again, you go ahead, every time I run, it's going to go ahead and pick one of these items or one of these quotes that we have here. So each time I run, that will happen. You can see the power now. We have a full application, a full container that's running. We containerize it, right? We created our Docker file. We specify all the directives that we want. And then we have the actual application, rather simple, but you can see that it works. So at this point here, it is indeed showing each time we run, it's going to show a different quote. All right. Very cool, very cool. So I hope you're seeing how wonderful this is. Now, if you have, of course, Python, which you should have installed locally, you could actually run locally, because this is running locally, but we actually are running the container itself. Because remember, we have, in this case, our Docker application, Docker desktop running. So we are running a container. This is not something we're running on our computer per se, right? We're running a container which is being served by Docker application or Docker desktop. That's really, really cool. So you can see that you can actually push this or send this image that we have here to somebody else out there, and they would be able to run your container and run this application on their machine or on their environment or server and so forth. Very, very cool. So that was your first step. It's very simple, as you see here. We have to have a base image. In this case, we are running on Python environment, so Python 3.11 Alpine, and I'll show you later why to choose that. And we have a working directory, and then we copy everything over to our work directory, which is the app. So inside of container, we have this app, that folder here, which in this case will have our app.py. Very good. I'm going to clear this. Very good. So this is indeed working, and there you have it. And of course, just like any other container, we can go ahead and say Docker ps-a, and you can see that it is indeed running. Okay, so we have, I think yes, it gave it its own name. That's okay. And it's running, and we can go ahead and delete it or stop. So Docker, I say remove -f. I'm going to just go ahead and get the container IDs. Could have used that to other way to get rid of everything at once, but that's okay. So enter, it's going to go ahead and clear everything. So Docker ps.a, you can see there's no running containers anymore. And if I say Docker images, you can see we still have our rand quote repository there that is working, right? Version 1.0. It's okay, we can just leave it as is. All right, very cool. All right, so we know that this is working because we tested out and the container is running from the image that we created. But this is too simplistic. So we want actually to be able to have a port where we can actually run this application on our container, and we can go to localhost and then see something a little bit nicer than this. Okay, again, it's very simple. I'm just going to show you real quick here so you can see the possibilities here, because everything now that we know that we can Dockerize this application following these steps here, and we can add a few more things as we add more files here. Okay, so we have app, very simple. I'm going to make this better. So I'm going to first of all go ahead and paste in a few other imports here, because we're going to be using Flask to create a very simple user interface for our application here, for our Python application. So for that, I'm going to also need to create a new folder inside of our application here, inside of our project, called templates. This is where we're going to be putting the HTML markup. So I'm going to just create yet another file inside there. I'm going to call this index.html. This is important. I'm going to put inside of templates. Okay. And by the way, you will have access to this project, all this code, so you don't have to worry about typing or anything. And so I already have the code for the index, and I'll explain a little bit. And so essentially here, this is the index file, which we're going to be serving. So that way we can just say localhost. Of course, we're going to Dockerize everything, create an image again, and then run as a container. And then we're going to attach, just like we've done before, attach the port, map a port, so we can go and be served, in this case, a quote. Okay, so now we have that. Now we have to go back to our app. So I'm going to just go ahead and change the code itself, and I will explain real quick. So most of it is still the same, but we have instantiated the app here, say Flask, because this is going to be a Flask application, and we still have all the quotes. And now we've changed a few things here. We're going to say app.root, because we're going to have the root here that will serve our website. So it's going to go ahead and define a function. So we have here a function index that is going to serve at this root here. That is going to be called whenever we go localhost / nothing, right? The root. And so we get in quote using random.choice, and we're printing that, of course. But most importantly, this is just for us right here. I'm going to go ahead and comment that out. But most importantly here, we actually returning, saying render template, and we're passing our index.html, which is this here. And then we're passing inside here. This is how you pass the information to, or render in this case, the information that we're getting from our app. So in this case here, we say quote, we're passing the object or the information we're getting, which is essentially is going to be one of these quotes. So we're passing it as a variable per se, okay, object into index.html. So that way we are able to invoke it by putting double curly braces as such. Okay, so essentially, once this is served, we're going to see something changing every time we refresh the page. Okay, that is the application. Now, that means then, in our Docker file here, we have to change also a few things. First of all, we still keep what we have, the base URL, or the base image, that is. The working directory, I'm going to change that to something else. I'm just going to say user / source. We could have left as was, but it's okay, and say app. Okay, and then we're copying everything onto our app folder or directory. And next we are going to actually install certain dependencies, because if you look at our app here, there are certain dependencies that we need, such as Flask. So that means then that I'm going to create yet another file, or another file here called requirements.txt. This is what's used in Python to run and install all the dependencies. So we list all the dependencies that our application need. In this case, our application needs Flask, and I'll just add the version, so 3.0.0. Okay. Okay, so we need to make sure that, of course, our Docker file knows what needs to happen, because we need to add that dependency right away when we are running when we're creating our image. That means then this is where I'm going to add the run pip install no cache directory and our requirement text. Essentially, it's going to go ahead and get the requirement.txt and run it and install the dependencies. In this case, we only have one dependency. And let's go back here. Let's see what else we need. Next, because this is going to be a web application now, we need to go ahead and expose. I'm going to copy this port, in this case 3000. So we're saying now we're exposing this container on port 3000. And of course, Python run app API or app py, which is going to be this file here. Remember, it's going to run inside of a container because it will know that everything is inside of our source/app directory. All right, so that's about it. So now what we need to do, I'm going to go back, open our command line here, or terminal, and I'm going to clear everything and delete even the image as well. In fact, I'm going to say, let's see, Docker images. Right, let me go ahead and delete that image. I'm going to say Docker RMI and just copy that. Okay, so Docker. Okay, we no longer have our image. That's okay. We could have left it and override it. That's okay. We're going to all right, so I'm going to go ahead and build our image because it's ready. We've made some changes. I'm going to say Docker build. Okay, I'm going to call random quote, and I'm going to say in this case 1.0 again and space dot. So this is going to go ahead and build our Docker file to create the image. Voila, very good. So there we go. We have everything now. And you can see this is the tracing of everything that has been done. And some of the things have been cached, so it skipped that, which is good. So it makes it faster. And we have the layers being exported and writing the image. So now, like if I say Docker images, we can see 73.6 megabyte, increase a little bit. All right, so we have our image. Now, because I know that I need a port, we're exposing port 3000 here. That's for the container. That means I need to map that port so I'm able to see this container running on a web browser. Okay, so now I can say Docker run. I can say -p. Okay, I'm gonna map the ports now. I can use 3000 and I'm gonna map it to the container port, which is 3000. And in this case here, I'm just gonna go ahead and copy the ID of our image and say run. Okay, and you can see now it says hey warning, this is development server, do not use it in production deployment. Okay, that's fine. And there we go. So we can go to localhost 3000. Oh, looks like we still have the old one. Let's go ahead to port 3000. And what do you see? Port 3000 now, it's serving our nice website. So if I refresh, each time I refresh, we can see awesome quotes are being shown here. The only limit to your realization of tomorrow will be our doubts of today. Very nice. So every time I refresh, I'm being served indeed a new quote. And as I do that, you can see as we run refresh, it is showing exactly that the get method has been called. The 200 response we're getting, that means everything is working correctly. That's why we're able to see those quotes being shown. And if I want, I could also open in a new command line or terminal in this case and say Docker ps-a. You can see indeed that it is running on port 3000, because that's where we mapped to port 3000 of the container. Of course, if you want to go ahead and stop, Docker stop, and we can get this random name that is given or the ID, either way that works. And you can see it should stop in a few moments here. Okay, so now it's stopped, which means if I come here and refresh, you should get a page not found or this site can't be reached. Okay, and of course the same thing. You can go ahead and actually remove. Okay, it's done. Docker images, you can see that the image will still be there, which is this one here. Now, the other thing we can do also, because we can see a repository here as name, we can also use, I'm going to go all the way to run this again. Notice here earlier I used the ID, but you can also just use the repository name, which is the name that we use of this image. But the thing is, we need to also pass the version tag, so 1.0. If you hit enter, the same thing will happen. So I usually want, it's always nice to use, in this case, the full name and make sure you add the tag to make sure this works. If we go back to 3000, we should be able to see that indeed this is still working. As we refresh, we still get the results. And if I go to that other tab, I can just Control C, and then it's no longer running. You can say Docker vs and Docker RM. I'm going to remove, in this case, pass the ID. Okay. Nothing. And Docker images should be able to see that we still have our random quote image there. We can leave it there. And just like that, we have changed or made this container, or rather this image, even better, right? Because remember, now we've added a few other things. This is Python related, but most importantly, notice that now we are running pip install because we need those dependencies which are found in requirements.txt. So all the dependencies your application will need will live here. And in our app, of course, we added that code that does what needs to be done. And at the end here, we have app.run on the host, and we have the 3000, which is the port that this will be running on. You are able to create an application, and then you're able to Dockerize it, containerize that application by creating an image. All of that is created by using the Docker file. And then you're able to build that image and then run your application from that image. That is very important. You're running your application from that image, right? The container in this case, right? You're running the container, which is hosting that application, has all the things that that application needs to run on its own. Okay, you're not running locally on your computer when you do that. You're actually using Docker to run that container. That is the distinction that we have to keep reminding you. That is the beauty of it. You can imagine that image I can send to anybody in the whole wide world. If they have Docker running, they can run our application without even knowing the code or having to tinker with the code. How beautiful that is. So it is indeed a package of our application that they can run it, and life is good. Love it. So now we're going to talk about base image optimization. Essentially, we're going to look at why is it important to optimize the base image that we're pulling in to create our own image. So if we go back to our command line or terminal in this case, we could, of course, use the terminal from our VS Code here, but I have this other one open. So either way works. So what I'm going to do is, let's say Docker, and I'm going to say images to give us a list of images. And one thing you'll notice right away is that we do have size here. And obviously, size is very important because as we create our images, we want them to be as light as possible, right? And it's very important. And this is why you see here we have Python. This is the base image. We say 3.11 in Alpine. So usually what you want to do is, let's go to our hub Docker or Dockerhub and search for different images. For instance, let's go for this Alpine here. So if you click on Alpine, it says here, it is a minimal Docker image based on Alpine Linux with a complete package index and only 5 megabytes in size. So Alpine, all things considered, is always a very small image possible, in many cases, for whatever it is that you want, for whatever images that you're looking to build or to run as containers. right? So that is very important. And the thing is, you can always look for any other image you're looking for. Let's go ahead and find Python, because that's what we were looking at. And you can see Python here. You can go ahead and pull Python as Python general image. But if you do that, of course, the images, of course, the size may be different. Let's go ahead and check it out. So if I go back here and I'm going to build this image again, by first of all changing, instead of Alpine, go ahead and comment that out. I'm just going to say from Python as such. So it's going to infer that we're just going to go ahead and pull Python image. And let's see what's going to happen. So I'm going to go ahead and run the same application in this case. So I'm going to go ahead and build an image, and we'll see inside. You can see that this is the random quote image that we built. We ran and worked fine, and it's only 73.6 megabyte. I'm going to go ahead and build again. Okay, so I'm going to say docker build-t. Let's call this random quote, and I'm going to give it a tag right away of 1.1 and space and dot. Let's see. So Docker now is going to go ahead and pull the Docker file and go through the process of pulling in. See, it's pulling in from docker.io, getting that image, the Python, and do all the things that it needs to create that image, right? So let's go ahead and clear. I'm going to say Docker images again. You'll see the difference. Now our random quote 1.1, which is the one that we just created right now, we have the ID 12 seconds ago. You can see it jumped to over 1 gigabyte. So that is a huge difference between 73 megabytes to 1 gigabyte. And so this tells you exactly that it's very important to always make sure that you are optimizing the base image. And you can always do that by going to the official Dockerhub and look for that image. In this case is Python. And you can always scroll down and see different tags. So each one of these tags will have a different size. For instance, we can look at Python slim, right, tag. So there's slim bullseye, but I'm going to stay at Python 11. Okay, so we can 11, you have 311 bookworm, we have 311 bullseye. Okay, let's try this bullseye and see what will happen. So 311-bullseye, and there it is. Okay, very good. So now that we have that, it's all saved. I'm going to do the same thing we did before. So build another image, and I'm going to change the tags here so we can see the differences. And each image that we're creating, if we were to actually run it as a container, it would run because everything else hasn't changed. All right, let's say 2. Okay, there we go. Now if I say Docker images again, we can see that the 1.2 tag, the latest one, 8 seconds ago, it's 886 megabytes. So it is indeed better than 1.03 gigabytes because it's 800, over 800. But it's still, we can see here that the slim, what we had before, which is this, I'm sorry, the 311 Alpine, it's still the best. So Alpine is always the best in terms of size. It's supposed to be very small. So there we go. Now we can continue to test because we don't know. Let's assume that we don't know. Let's go ahead and check the slim bullseye, 311 slim bullseye. Okay, there we go, slim bullseye. I'm going to go and use that, and we'll do the same thing. And 0.3. Okay, say Docker images again. All right, so by building our slim bullseye, we reduced to 137. Still not as good as Alpine, right? But you can see now it is smaller than the previous one. So that is something to keep in mind. And in this case here, we're going to go back to what we had before, which was Alpine. Save, and let's go ahead and build that just because. And this is going to be 0.4 and should have the same size. And there we go, 73.6, which is exactly what we had before. Okay, so there we go. So keep in mind that it's always important to keep your images very, very minimal in terms of size, because the heavier the image is, first of all, if you're sharing with people, the more reluctant they will be to download and install your images. So efficiency is very important, especially when it comes to the image size. So once you've created your images, you can then publish them to Dockerhub. Now this is beautiful because then once you publish to Dockerhub, you're able to have other people from all over the world being able to pull that image and run those containers, which means they will be able to run that application. That is indeed the power of Dockerhub and being able to publish those images we create. So essentially, right now we're going to go ahead and learn how to author and publish our own images to Dockerhub. All right, so if you go to Dockerhub, so hub.docker.com, so you can see right away that I'm actually logged in, right? Palo Cloud Dev. And if you go to repositories, well, this is just me, you'll see that I do have a few images that I have authored over the years, and this one that I authored a few weeks ago, almost a week ago. But you notice that the first thing you need to do in order for you to be able to push images to this registry, to this registry here, Dockerhub, you'll have to create an account. Dockerhub, and then you have to sign up. So click sign up. And it's very simple. Of course, you'll have to either create an account you continue with Google or with GitHub, or you can just go ahead and add email, password, and so forth. Okay, I'm not going to do that because I already have, but once you have an account, you will be able to see something like this. So you'll be able to log in and it should be good. And the other thing you would want to do, of course, is to open, in this case, your dashboard for Docker application. And what you want to do is you would want to actually go ahead and log in. So you can see that I am logged in. So I'm signed in. You want to log in once you have an account so that everything is synced up with your Docker desktop. So just something to keep in mind. Okay, so that is the very basics of Dockerhub. So make sure that you have an account. It's free. Of course, you can have enterprise accounts, but you can have a free account as well where you don't have to pay for anything, which is the one I have. All right, so in the next video, we're going to see how can we author our own images and push them to our Dockerhub account. Once you have created your Dockerhub account, you should be able to log in and it should have something similar to this as your profile name. Okay, so once you do that, then we're ready to author our image and then be able to push to Dockerhub. Going to use our previous random quote -1. This is the project we've been working on that only serves random quotes. Okay, so we're going to make sure that this is okay and then go through the process of building it and then first of all test locally again, just make sure it works, and then build it as well as then push to Dockerhub. Right, as always, I'm going to go ahead and build this. I'm going to say Docker build. I'm going to give it a name. Now, because you should have your profile name, your Docker profile name, now we're going to use that profile name or account to create our image. So it is best practices. So in this case here, I'm going to use -t, call this Palo Cloud Dev / in the name of our project. So in this case, we call this random -quote -1, and then I'm going to give it a tag 1.0. Okay, so if you don't give a tag, okay, it will go ahead and give a latest, which is fine as well. Okay, let's go ahead and hit enter. Right, I forgot to put the dot at the end. Okay, let's go ahead and do this. Now it's building, and it was really fast because most of the things were cached. So that way the layering went fast. First thing you can see, the layer was added 1 out of 4. So got the from image, base image, Python 3.11 Alpine, and then everything else was cached. So work directory was cached, copy and run were all cached because that has happened before. So that's really good. That's the reason why this went fast. So now I can say Docker images. We should have indeed our image. So we'll see here Palo Cloud Dev. Again, make sure that you use your own account ID or account name or profile name when you do this. Let's go ahead and run this real quick just to make sure again that this is working. So I'm going to say Docker run. I'm going to just put P, and I'm going to map the ports 3000 in the container, and I'm going to use, of course, this is the username that I'm going to be using, or that was attached, of course, to my image. And I'm just going to put 1.0, of course. So I'm going to run, and you can see now it's running to localhost 3000. And you can see that it is working perfectly fine, which is really awesome. Okay, so we should be able to see this locally. And of course, you can see that everything is good. So I'm going to go ahead and Control C just to get out of this. And of course, as I said, you can use our terminal that's open as well, but you can also use, of course, the terminal that is attached to Visual Studio. Okay, now that we already have built our image, we can go ahead and push that image. Before we do anything, we need to log in, make sure that we are logged in with our Docker ID. So what you can do, just say Docker here, log in, hit enter. And because I'm already authenticated, you will see that login is successful. In your case, it probably will show, it will probably direct you to a web interface where you can log in using your credentials that you used to create your Dockerhub account. So go through that process, and you should come back here and you should see login successful. It's either that, or you will have to actually add here your username as well as your password, right? One of those. You should be able to do that and then be logged in. So now that I'm logged in, succeed here, that's when I can say Docker push and push my image. So first of all, I'm going to say Docker images, so to see the images. You can see that is the image that we have here. Okay, very good. And now I can say Docker push, and then make sure you are using the exact ID, right, that we created. So that's the ID for the image. So I'm going to also say 1.0 or 1.1, just give it a tag. If you don't give it a tag, what's going to happen is it will give a tag of latest. So I'm going to just give it a tag 1.0. Okay, so hit enter. And now it's preparing everything. And then was able to push all of that. And how do you know that this has been pushed? Well, let's go back to our Dockerhub. Make sure you're logged in. I'm going to refresh and then go to repositories. These should be your repositories. And what you see here, we do have random quote. Click here, and there we go. So we have version 1.0. So that is the tag name. And voila. Now, notice that this is actually the public. This is what you see as the owner of this image. If you want to see what the public will see, so you can open this on a new view here. That's the public view, and voila. So you can see it's very simple. And we have this should be your profile name, and then the name of your application. But most importantly, if you go to tags, they're going to be able to say that the tag is 1.0. And the great thing is they can actually copy this, as you can see, and pull that image and run our application. Now you can see here, it's customary to be able to add more information about our applications. In this case, I'm going to manage repository, and then I'm going to go and add an overview of this application, what it does and how to run it and so forth. So you can write something a little bit more extensive than this. Of course, this is just simplify, and I can say preview. You can see that it shows exactly how it would look like. Okay, here when you write, this supports Markdown. Okay, so that's why you can see this field preview. You can have this information highlighted with different format, right? So it's really good. I'm going to leave it as it is right now. Of course, I'm going to change that later, but you make sure that you add all the information you need so that people who come to look for your awesome image, they know what the image is about. So I'm going to say update. And there we go. Okay, so if you go to tags, you can see there is a tag, and general, it tells us a little bit about the tags. There's just one, and that information we just added here. Okay, that's very good. So the question is, okay, how do we test this to see if it works? Right, it should work, but let's go ahead and test it. So we're going to go ahead and pull our image that we just uploaded here and locally, and run locally and see if this works. So first of all, I know that I'm going to go to the public view again. You can see here it says Docker pull command. I'm going to copy that, and then I'm going to go to my terminal. I'm going to first go ahead and say Docker images because I want to be able to delete all of them. So we have this running. I'm going to say Docker RMI. I'm going to force it because I know it's running. So I'm just going to go ahead and let's just get the ID for now to simplify our lives, and delete it. All right, so now we know that it is indeed gone because we don't have images, and I can say Docker PSA to see if anything is running. Yeah, that is has exited, but I can also get rid of that. So I can say Docker RM and pass in the image ID again, just to clean things up. Oh, that doesn't look right. Let me get this one, container ID. Let's just get the name perhaps. Okay, there we go. Now it's gone. So if I run this again, we know that it's gone. All right. So I'm going to go ahead and pull that image and paste. Okay. So Docker pull, there we go. It actually added the 1.0. That's very convenient. I'm going to pull that image. We could have also said Docker run, and then this would have done the same thing, as you know. And voila, now we can say Docker images just to see what's going on. Voila, we have our image. And because of caching and everything, it went ahead and pulled what we had before. That's okay. That's totally fine. But we know we have something that we pulled in. So now I'm going to say Docker run P. I know it's the container port is 3000. So I'm going to go ahead and localhost 3000. So 3000 to the container 3000 port. And of course, I'm going to make sure that the name, which is this, is what I'm going to add there to run this. I'm going to go ahead and run. Oh, right, I have to put, of course, 1.0 because that is the name we added. Okay, let's go ahead and run now. So you can see that this should be running on port 3000. I'm going to go ahead and open a new tab here. Say Docker PS, just to see what's happening. And indeed, we can see that we have on port localhost 3000, which is mapped to the container host, the container port 3000. All right. Let's see if this works. Let's go ahead and see if this is actually work. I'm going to refresh. This was from previous one, but now you know that it's still working because this is from our fresh added image, pulled in image. Very good. So just like that, you're able to take your project, containerize it, build it, and then create an image and then push that image for the world to see and use it. So now if they go and look for Paulo or random quote. There we go. There we go. All right. Now you can see that indeed this is working. And if we go to, you can see that there is one poll, right? That means it tells us exactly that people have pulled. So as people come and pull your image, this counter will go up, which is really awesome. But also can go to repositories and you can see that I have one poll here. Okay, very good. So this actually tells you that indeed we were able to pull it and run locally and see that indeed this is still working. I hope you're seeing how easy this is to create very simple applications, and you containerize those, right? Dockerize those and then create an image, and then you can push those images here into Dockerhub, assuming you have an account, and anybody in the world can go ahead and get this image and run it, and they can look at the application, the wonderful application that you've built. Very, very cool. Very cool indeed. And keep in mind, they don't have to have Python or anything installed on their environment. As long as they have a Docker runtime, they can do exactly what you saw me do and run this container and of course be able to use our application. That is the beauty of containers, is that we have that flexibility. All right, so in this section, we talked about Docker files, images, and publishing. So here's a summary of what we covered. So we actually covered a lot in this section. So we talked about Docker files and images and how they are structured, in this case, directives, and the structure of Docker file, which is the file that is used to create an image. And we're able to actually Dockerize a very simple web application, which was really fun, as well as we looked into Docker image optimization, because we know that the smaller an image size is, the better it is for portability and so forth. So that was an important part of understanding about Docker files, images, and of course publishing. And yes, we looked into publishing images to Dockerhub. So essentially you had to create an account with Dockerhub and we're able to build those images from, of course, our Docker file and then publish them. So we are making good progress and I'll see you next.